Hi there. In this tutorial, we want to go through the calibration probability concept. For that, we need to look in Platt paper from Microsoft Research, and its concept still being used in various machine learning applications. But what is the calibration probability? So the calibration probability is one of the concepts that we need for having a better generalization. And when performing a classification or even a regression, we want to predict not only the class level, but we want to predict the probability. And probability give us some kind of confidence of the prediction. So if we have a binary classification, this is one hard encoded, we know that the argmax of uh, the output can be used for the label. But the value here are important for us. So based on the method that we train the model, like maximum likelihood or stuff like that, we can have a confidence level. So if I have something like 0.6 here and I have something like 0.4 here, so the class number 0 is selected, but the confidence is not high, and a small change in input can change the output. Calibration, which means that we want to map these two values if we are sure that this is right. We want to map these 0.6 to like, I don't know, 0.9 or even 1. That depends on the problem. And we want to set this to like 0.0 or 0.1. So this is a mapping that we want to do this. And the reason is that if we have some change in the input, maybe some noises, we don't want to have false prediction. So the main purpose of the calibration is to have a better generalization and also having a better confidence when we want to do decision making about the output of a model. This paper here is introduced by Microsoft Research in 1999 by Platt, and this is famous as a Platt calibration. And this is one of the first papers that bring the calibration probability in classification. And we have different type of calibration. One is the binary classification calibration, which is the simplest one. Then we have multi-class classification calibration, which is usually like a binary classification approach, but we do multi-class as one against rest of the classes. So if we have deep learning approach and if we have machine learning approach, um, the way that we look into the probability is different. That in machine learning also that depends on the process. Like here it said that training with the maximum likelihood score will produce non-sparse kernel machine. And that's why they train the parameter of additional Sigmoid function to map the stream output into probabilities. We have some data here and some data here. And using the SVM, we are creating a support vector to separate these two, but it is not giving a probability. It's just calculating a separator plane, and these kinds of model doesn't have any probability output. The way to calculate the probability is usually applying a softmax layer, or here they said they applied additional sigmoid function here. They are converting the output with another layer here. I can maybe call it F. So we are applying F on the output of the model, and we try to calibrate it. For deep learning, also we have different approach and different problems. Like when we have a neural network here, it can be any type of classification or regression. If we have any input here and we get the output, and if the problem is in binary classification, we have two outputs. We call them logits, and we apply softmax to calculate the probability. But many papers and research talk about that applying just a softmax is not reflecting the confidence of predicting each of the classes. So one of the way that they applied is we have dropout in training, and if we active those dropout randomly, like this layer here, or maybe even this part of the network, and we have a dropout and we feed the input to the network and get like 10 different outputs because of the variation of the dropout. By getting the average of these outputs, we are getting more realistic probability from this network for each of the classes. So the paper as I mentioned, is applying a sigmoid layer at the end of the SVM to do calibration. And it is really simple. You can see here that they said the class conditional density between the margins are apparently exponential, and Bayes rule on two exponential suggests using parametric from a sigmoid. So the F is the output of the SVM or any machine learning model. What we want to do is predicting the A and B. We have Y, I, which is the target of the model, but we need a target of the probability. So in this paper, it said the target of the probability can be defined here. Yi can be 1 or -1. It wanna minimize the negative log likelihood of this while the sigmoid function is defined here. So it's so simple. If we have the derivative of this one, we can have gradient descent and apply that to find the A and B. If we suppose that we have a data like we have train and test. So this is a training part and this is a test part. And we apply the training for label prediction or for classification task, and we train the model based on this data and apply on this. We should not have the same data set for calibration. The best way is to have like cross-validation. So we train this on this part of the data, and that's better to not be from the training set because that bring the bias. So it's better like to have this test set here and apply the cross-validation on it for calibration. We will go through this implementation. We will not implement it ourselves. We use the Scikit-Learn, but we will show the code that how it is working. And another paper came in 2017 talking about beyond sigmoids, how to obtain well-calibrated probability from binary classifier with beta calibration. It's showing a graph here showing the different way of probability calibration. We talked about one of them, which is the Platt scattering and applying a sigmoid. But instead of sigmoid, people also use logistic regression at the end of the same as applying a sigmoid, but instead of the sigmoid kernel, we are applying the logistic regression. Another way is the isotonic regression. The isotonic regression is introduced by Zadornzi, if I spell correctly, and his partner Elkan. And the title of the paper is Transforming Classifier Score into Accurate Multi-Class Probability Estimates. It is published in 2002. They mentioned here, if you see the previous paper, the Platt scattering, and you see that there is a sigmoid shape. And these papers say that one of the reasons that the Platt scattering was good for the SVM is usually the output of the SVM is following the sigmoid rules. So it said that the parametric approach proposed by Platt for SVM score consists in finding parameters A and B, as we said, for a sigmoid function. And the method is motivated by the fact that relation between SVM scores and empirical probabilities appears to be sigmoidal for many datasets. Like in adult dataset that they use or in other dataset that they showed, that relation, the empirical probability and the SVM score are like a sigmoid function. That's why other people use the logistic regression to be more generalized, but logistic regression for calibration may give overfitting. So isotonic regression is a regression that every sample is greater or equal than the previous sample. So we always have a ascending series. Instead of saying that the scores of the classifier is based on the sigmoid function, we can always sort the scores and we can apply isotonic regression. So if you see the isotonic regression in Wikipedia, you can see that it is like a bean approach. This part is like a bean. So this line here is like taking average from all these point confidence level. Beta is, as I said, is introduced in 2017 and it's better than the sigmoid. And if you see the figures, you can see that isotonic regression is good somehow. but the beta calibration is better. I forgot to say that one of the advantage of isotonic regression is that if we don't have more than 1,000 samples, it can be good. So if we are using few samples, the isotonic regression is the way to go. But if we have more than 1,000 samples, we can use other methods like the beta calibration here. So let's do some implementation about probability calibration for binary classification. And we are not implementing the calibration from scratch. We are using the Scikit-Learn library and also code from the probability calibration curves documentation. So you can go to that page and see the complete code. But here we just want to walk through some of that, and which is not like previous session that we write the code from scratch, but we are trying to convey the meaning of the calibration probability. I can import the data set and the model selection train test split. And I want to use 100,000 data with 20 features. So I have X, which is, as I said, 100,000 with 20 features. So I don't need number of informative, and number of redundant is the number of redundant feature. These features are generated as a random linear combination of the informative features. So it's just increasing the complexity or difficulty of the classification if we have correlation in features. So maybe just 2 is okay, or maybe we can also use a default. And random state is good. So the next part, we want to split this data to train and test. We want to like have test size 99%. So the reason that we are doing that is we want to show that the calibration can be applied on a small part of the data. So only 1%. 1% is 1,000 here. I have 1,000 rows. So as I said, we need at least 1,000 sample. So documentation also used the same. And for these 1,000 sample also, we can apply cross validation. I want to have a logistic regression. I need to define a logistic regression. And the C I define here is 1. It can be any other parameters that you like. And C is the inverse of regularization strength. So if we have like C1, we don't have a regularization, and a smaller value specify a stronger regularization. So there is a function calibrated classifier CV. We need to import it from Scikit-Learn calibration and calibrated classifier CV. And we can say, what is a CV? I want to like apply cross-validation to it. Means I split the data to 2 parts. We can pass the method. Method we can apply is a logistic, can be Sigmoid and Isotonic. So we need a classifier. What classifier can we use? We can use SVM because this is classifier. We can use SVC. The documentation implemented something interesting that we can have SVC, but on top of the SVC, we can have our customized calibration without using the logistic regression or Sigmoid or Isotonic. So we use functions that defined in the documentation. It's called naively calibrated linear SVC, and is inherit from the linear SVC. So we can do super.fit in the fit function because it is override function for the linear SVC. And after that, we calculate the mean and the max of the decision function. And the reason for that is when we have an output, we want to normalize it using the linear transformer here. So we have df minus minimum of df divided by maximum of df minus minimum of df. And this is a calibrated, and we found the positive parts of the normalized calibration and negative return a probability. What we want to do is we, like here, we can have naively calibrated SVC. So we can use that to be calibrated by these 2 methods, and we can call it like isotonic SVC and sigmoid SVC. And because we have like 4 different classifiers, we can put them in a list. It can be a tuple with their names and with the classifier. So this is a logistic regression, and the name is logistic regression. So we have this list, so we can apply for loop on this list each time, just train a classifier using the training data, xtrain. Beside of calibrated classifier, we can have calibration display, and that calibration display can be used after we train the model. So we can say calibration display dot from estimator, and here we can say the name of the classifier. Then we can apply the test and by test to see how the calibration works. So there is a code in documentation, we can use that. So this is the result of what we have done. So we have naively calibrated linear SVC, which is this one. You can see that this is not calibrated, but after we do the calibration, like using the isotonic regression or using the sigmoid, you can see that this is calibrated. So it means that it has a good confidence on predicting something is positive or something is negative. And here it can show that this line, the dotted line, is the perfectly calibrated, which means the average of predicted probability is equal to the fraction of the positives. So the good calibration means that when we say something like 80%, we should have about 80% of them in the data. And this is on the test because we are applying it on the test set. The test set is too big, but still we see that the calibration works very well. And you can see this is like a sigmoid. That's why in the first paper, as I showed, sigmoid method works very well. And also you can see the sigmoid, which is the pink one. It is fitted very well respecting to the isotonic, which is not like the sigmoid because this shape is really similar to the sigmoid, but still the isotonic is very good too. So this is a way that we can apply the calibration on the data. If we back here, the only modification we applied on the SVM or SVC to be calibrated with the sigmoid methods is finding the probability. It's like we have two outputs. The first showing the probability for class 1 and the second is showing the probability for class 2. So this is just a trick to convert the output to the probability. So the final point that we want to make is looking into the Scikit-Learn calibration class in the GitHub page to see how they implemented that and compare it with the paper, and you can understand that it is not too hard to implement it ourselves. The way that they are applying the sigmoid calibration is here, that we define an objective. Objective is, you remember that formulation for it, it said minimize the negative likelihood, and this is the same formulation. And for that, they are defining the loss and calculating the gradient of that loss. And using fmin BFGS in scikit-learn can find the minimum of a function. So using that, they are minimizing that objectives to find the AB. The final things they return is A, which is the index of 0, and B, which is index of 1. They can support regression too, which is good for sigmoid calibration. And if you see that, it is exactly using same sigmoid calibration function. Another thing that they have is isotonic regression. It is just applying a isotonic. It means we have some data, like here, we can fit some input to the output. So if we have our estimated probability and we have our desired probability, which is 0 and 1 based on the positive and negative samples, we can fit some input to the output. So remember that we have converted the output of the model to two output. One is related to negative and one is for the positives. And what we can do here is if something is positive coming here, this output should be 0 for it. And if it is negative, it should be 1. So we are doing a regression on this for changing their value. It can be changed independently, but their sum should be equal to 1. This is one way of looking to this problem. This is exactly the same way that the multi-class classification is also solved. That, for example, we have 3 class 1, 2, 3. We apply regression 1 against all So if it is correct, we say it is 1. If it is not, we should set 0. And after we predict them, we just normalize them to have sum on these should be equal to 1. You can see here that they are checking that if, say, method should be isotonic, they just apply the isotonic regression as a calibrator. Otherwise, they are using the sigmoid calibration. And on the fit function, you can see that there is this prediction, and we have the class index. So for each class index, we are applying a calibration, and we append that calibrator to the system. So based on how many classes we have, this method can be extended. That's why the Scikit-Learn is working for multi-class classification. This is 1 versus all. So this is how they apply the isotonic regression and sigmoid regression for calibration probability. Of course, if the problem is regression, the output is same as the probability that we are predicting, and it's like we are applying another layer after the last layer of prediction. Thank you and have fun.